Okay, now let's take a look at the concepts of solving equations with rational expressions. Solving equations. So equation solving skills is what we need here. We're solving equations with rational expressions. Again, these are the fractions that we've been working with in this chapter. Excuse me. All right. Now, the technique we're going to use for solving equations involving rational expressions is the same technique that we used back in, for example, back in section 3.2 in chapter 2 of your text here, when we solved an equation involving a fraction. For example, let's say we're asked to solve this equation here: 2/3 x minus, let's make it minus 4/9 is equal to, let's say, 5/6, for example. All right. Now we've seen an equation like this back in chapter 2 here, section 3. Chapter 3, excuse me, back in section 3.2 in particular. All right. Now, how do we approach a problem like this? Well, we said, all right, well, we're going to get rid of fractions. Notice we're going to get rid of these three denominators by multiplying each one of these guys by the LCD. So basically, we're multiplying both sides of this equation by the LCD to get rid of these denominators. All right. So that's the theme we'll use here. That's the concept we'll use here to solve equations involving the types of fractions that we've been working with, called rational expressions. All right. So let me say that. Let me say here: multiply both sides by the LCD to eliminate fractions. To eliminate fractions. Okay, so we're going to multiply both sides by the LCD, the lowest common denominator, to what? To get rid of fractions here, if you will. Okay, so to get rid of fractions here. All right, so let's go ahead and do that then. So let's go ahead and look at the LCD here. So 3, 9, and 6. What's the LCD going to be in this example here? Well, if you think about it a little bit, it's going to be what? It's going to be 18. What is the least common multiple of 3, 9, and 6? Can we say that's going to be what? 18. Can we see that? All right. So let's multiply both sides by 18. In other words, let's multiply all three terms by 18. Multiply 18 to all three fractions. All right. So we get, again, we've done this before back in chapter 3.2 in particular. Right. So 18 times the first fraction, 2/3 x. All right. Minus 18 times the second fraction, 4/9, equal to 18 times the right-hand side, which is this 5/6, just that one fraction there. All right. Okay, then, so let's work it out. So what do we get then? Well, we're going to get what? 3 into 18 here is going to be what? 6 times. So 6 times 2x will be what? 12x. All right, can we see that? All right, 9 into 18, twice. So 2 times 4 will be what? Minus 8. All right, equal to 6 into 18 here will be what? 3 times. So 3 times 5 is what? 15. All right, can we see that? So therefore we get a nice, after I multiply both sides by the LCD to eliminate fractions, look, I get a nice easy equation which I can finish solving, right? So add 8 to both sides here in this case. Okay, make sure we see that, not too bad. So 12x is equal to what? 23. So dividing both sides by 12, then we have our result here of 23/12. So therefore x is equal to a fraction answer of 23/12. All right. So again, the theme here is what? In this section is what? To solve equations involving rational expressions, we're going to do the same thing. We're going to multiply both sides by the LCD to eliminate fractions, to get rid of these denominators, namely. All right. So let's look at a problem involving the fractions in this section here. Let me go and clear off the screen. So keep this concept in mind. Let's go and try this one. All right, let's look at 3x minus 1 over 4x. All right, plus x there, sorry, plus 2 over 3x. All right, equal to 7 over 6x. All right, not too bad. Let's look at these three denominators: 4x, 3x, and 6x. Again, we're going to multiply all three of them by the LCD to get rid of these guys. All right. So what is the LCD then? Well, hopefully, after thinking about it a little bit, you see the LCD will be what? Well, 4, 3, and 6. Least common multiple, 12. x, and x. Well, just x then. All right, can we see that? So the LCD is going to be what? 12x. Can we see that in this example here? So let's multiply all three fractions by what? 12x to get rid of these three denominators. All right, so let's go and do that. So 12x times the first fraction, 3x minus 1 over 4x. All right, plus 12x times the second fraction, 2 over 3x, equal to 12x times the third fraction, 7 over 6x. Again, I'm multiplying everything by the LCD to get rid of those three denominators, right? To get rid of fractions, in other words. All right. So let's work it out. So 4x into 12x, how many times? It'll be what? It'll be 3 times. Is that right? X's drop off, 4 into 12, 3 times. All right. So I get 3 times 3x minus 1. I'll do it in 2 steps. You can also distribute 3 here if you want to, but I'll do it in 2 steps. All right. 3 times 3x minus 1. Can we see that? And 3x into 12x, how many times? Well, 4 times, right? 3 into 12, 4 times x's drop off. So plus 8 equal to 6x into 12x twice, all right? So again, x's drop off, 6 into 12, 2 times. 2 times 7, 14, all right? Once again, get a nice equation to solve after I've eliminated the fractions, eliminated the what denominators, namely. All right, let's finish this off. So 3 times 3x would be what? 9x. 3 times negative 1 is negative 3, plus 8 equal to 14, all right? 9 combined like terms, 3x, negative 3 plus 8 is what? Positive 5 equal to 14. Subtracting 5 on each side. Again, make sure we're sharp on solving these basic equations here. We've done these equations before in the past, right? So we get 9x is equal to what? 9. So therefore, x is equal to 1 if I divide both sides by 9. So x is equal to what? All right, x is equal to 1, as I mentioned. All right, so there we have it, right? So again, the theme is what? Multiply both sides by the LCD to get rid of fractions. After I do that, I get a nice, easy equation to solve here, and I finish solving it. I get 1 as my solution here. All right, and we can also plug 1 back in for x to check our answer. Okay, but I'm not going to do that for you here. But you get you get the idea. All right, let's try another one. Let me clear this out. Let's look at this one. Let's look at x plus 1/3 is equal to 4 over 3x. All right. So let's multiply everything by the LCD to get rid of the 3 here and the 3x here on the bottom. So how do I do that? Well, what's the LCD here? Hopefully we see it's going to be what? 3x. Can we see that? All right. So let's multiply all 3 terms by 3x. So 3x times x, all right, which is 3x squared, of course, plus 3x times 1/3 equal to 3x times 4 over 3x. Again, I'm multiplying the LCD to all 3 terms here, all 3 fractions here. Can we see that? All right. So I mentioned 3x times x is 3x squared. No big deal there. All right. 3's drop off. All right, cross cancel there. So x times 1 is x. So plus x equal to 3x is canceled completely. So equal to 4. All right. Are you with me on that? All right. Well, we've solved this equation before back in section 8.5. You remember, right? That's a polynomial equation. We have to solve it by factoring. You remember that, right? 8.5, right? In particular. So to solve by factoring, though, first I need to what? Zero out one side. Zero out the right-hand side in this case. Let me subtract 4 on both sides to do that. So that takes care of 4's. So now I have 3x squared plus x minus 4 equal to what? 0. Okay, can we see that? All right, let's factor this then. Well, factor it by trial and error because we have the 3 in front of the x squared, right? So 3x and what? And x for 3x squared. Can we see that? All right. 4, I'm thinking of 2 and 2 here. Okay, so is that going to work? Let's see here. Let's try that. See, 2 and 2. Will that work? Let me see here. 2 and 2. Well, that's not quite going to work. How about let's try this. Let's try a 4 here and a 1 here. So I'm doing the mental arithmetic and for trial and error, right? So I want to get the right combinations. So 4 here and a 1 here. Is that going to work? Well, let's see. Let's check the middle. So this is what? This is 4x. This is 3x. Ah, it's going to work out. So see that 4x and 3x. Can I get a positive 1x out of that? Yes, I can. Again, review the factoring in Chapter 8 if you need to, right? This is just solving the equation by factoring. No big deal. Now, I want to get positive 1x. So I need positive 4x to make that happen. And what? Negative 3x to make that happen. Okay, again, 2 and 2 didn't work, but 4 and 1 here does work. All right, and then what? And then if you remember from 8.5, what do we do? Well, we set each factor to 0, right? So 3x plus 4 equal to 0, or x minus 1 equal to 0. Right? Here we're going to subtract 4 on both sides then to solve each equation separately. So 3x is equal to negative 4. Are you with me on that? All right. Then divide both sides by 3 there. Sorry to squeeze that 3 on the bottom on you there. All right. So we get x is equal to what for this part? Negative what? 4 over 3. So negative 4 thirds as one of my answers. Right here, I just add 1 to both sides. So no big deal here. So x is equal to 1 as the other answer. So we have two solutions here, right? So the solutions are negative 4 thirds and what? Positive 1. Okay, can we see that? So you may have two solutions for solving these types of equations here. Okay, let's look at another one. Let me clear up the screen. Let's give ourselves plenty of practice here. All right, let's look at 5x over x plus 2 equal to 3 minus 10 over x plus 2. All right, let's take a look at this equation. All right, what's the LCD going to be? Well, this is 3 over what? Over 1 if you want. Put it over 1. All right, but the LCD will be x plus 2. Hopefully we can see that without too much trouble there, right? That's the LCD, right? All right, so let's multiply everything by x plus 2. So x plus 2 times the first fraction on the left side, 5x over x plus 2. On the right side, I'm going to have x plus, well, let me put 3 in front if you don't mind. 3 times x plus 2. That looks a little better, okay? And then x plus 2 minus, so here's a minus sign here. Let's bring it down, all right? X plus 2, my LCD, times the last fraction here, 10 over x plus 2. Okay, so we're good on that. So the x plus 2's drop off, as you can see here on the left side. I just have 5x equal to, let me distribute the 3 here. 3 times x is 3x. 3 times 2 is going to be positive 6. Here the x plus 2's will cancel directly there. You see that? So minus what? Minus 10. All right. Again, nice easy equation to solve, right? So 5x equal to 3x minus 4. Okay, we see that combining like terms there. So subtract 3x on each side of the equation. Okay, so I get 2x is equal to what? Negative 4. Then dividing by 2, I have my solution here as x equal to what? Negative 2. Can we see that? Now, let's plug this back in just for completeness. Let me plug in negative 2 back into the original. Again, your solution should satisfy the original equation. In other words, if I plug in negative 2, it should make the what? Left side equal to the right side. All right. But look what happens though. When I plug negative 2 in to this fraction right here, what happens? Well, 5 times negative 2 is what? Negative 10, so that's okay. But look down here. What is negative 2 plus 2? What's negative 2 plus 2? Isn't that 0 down here? Uh-oh, that's a problem, right? Can we see that? So we cannot have 0 in the denominator. So in other words, the answer of x equal to negative 2, when I plug it back into the original equation, it makes the denominator down here 0. So that means what? That's impossible, right? Because you can't divide by 0. That's undefined. So therefore, is this answer x equal to negative 2 valid? No, it's not. This is not valid. Okay, not valid since it makes the original fraction or fractions, right? In this case, it makes both of these fractions what? Undefined. Okay, so again, this solution is not valid because when I plug in negative 2 so my answer is negative 2 here. When I plug it back into the original, I will get what? I will get 0 in the denominator. Negative 2 for x plus 2, 0. Negative 2 plus 2, 0. And we can't have that for a fraction to have 0 in the denominator. That's undefined. So therefore, this answer here is not valid. So in this case, then, we have what? No solution to this equation. So you may get no solution here. Right? So what you need to do is, though, when you solve it, you don't have to check it very thoroughly, but you just have to plug it. Just compare your answer by plugging it into what? The denominator. Make sure your answer is not causing the denominator to be what? To be 0. Otherwise, it's undefined then, right? So no solution here. Okay, can we see that? So this one we have to pay attention to. Okay, so again, be careful here on these equations. Let's try another one. Let me go clear out the screen. Okay? So again, think about these equations carefully here. Okay. So let's try this one here. Let's look at 8 over r plus 3 over r minus 1 is equal to positive 3. All right. So again, let's multiply everything by the LCD to get rid of these two fractions. In particular, this is 3 over 1, right? So what's the LCD going to be? Well, hopefully by now we're sharp in recognizing the LCD given these rational expressions. It's going to be r times what? R minus 1. Can we see that? One different factor, another different factor. Their product is the LCD. Okay? Make sure we see that now. So let's multiply this to all three terms here. Okay? So r minus 1 times the first fraction here on the left side, 8 over r, all right, plus r minus 1 times the second fraction here, 3 over r minus 1. All right, I'm running out of space here. So this is equal to 3 times what? Times r minus 1. r minus 1. Sorry to squeeze it in on you on the edge here. So hopefully you see it. Again, I'm just multiplying r minus 1 to all three terms. Hopefully we can see that. Sorry about writing so close to the edge here. Okay? All right. So let's work it out. So here, what's going to cancel out? Well, the r's will drop off. Can you see that? So I have 8 times r minus 1, right? Let me go and work that out as well, if you don't mind. So 8 times r is going to be what? 8r. 8 times negative 1 is what? Negative 8. Can we see that? All right. So I combine a couple of steps there. All right. So here, r minus 1s do drop off here in the second fraction. So 3 times r, right? 3r. Okay, no big deal there. Here I have what? I have 3r times r minus 1, right? So this is going to be 3r times r is going to be what? 3r squared, okay? 3r times negative 1 is going to be what? Negative 3r. Can we see that here? No, it's a little bit close to the edge, but again, here I have 3, right? If I tack on r minus 1, which is the LCD, then I have 3r times r minus 1. But 3r times, so distribute that. 3r times r, 3r squared. 3r times negative 1, negative 3r. Okay, are you with me on that? All right, let's combine like terms here. 8r plus 3r is going to be what? 11r minus 8 equal to 3r squared minus 3r. Okay? That's an r right there. Okay, so what happens next? Well, again, I see a square term for r. So that means what? When you see a square term for the variable, you're thinking, okay, I want to solve this by factoring from section 8.5. This is not a linear equation because r is being taken to the second power. So let's go and solve by factoring, right? So how do I do that? Well, to do that, again, one side has to be 0. But since the r squared term is on the right side, let's make the left side 0. Let's 0 out the left side completely. Right, how do I do that? Well, first of all, let me get rid of the 11r by minusing it out, subtract it out. All right? Let me combine a couple of steps here, because what else can I do to get rid of the minus 8? Well, how about plus 8? Both sides again. What separates the two sides? The what? The equal sign. All right? So that takes care of that. So I have 0 equal to what? 3r squared. This is minus what? 14r plus 8. Are you with me on that? All right? So let's solve by factoring, all right? So 0, let me write over here because I'm running out of space. 0 is equal to what? Let me make two sets of parentheses here for trial and error factoring. 3r and 1r for 3r squared. Are you with me on that? All right. For 8, I'm thinking of 4 and 2. So let me put 2 here and a 4 here. Is that going to work? Let's see. Excuse me. So let's check the middle term. See, that gives me what? 2r. This gives me what? 12r. 2r and 12r. Can I get 14? Yes, I can. But I need to make them negative. So negative 2r and negative 12r will give me negative 14r. So this is the correct factoring for what? For this problem here. Okay, for this polynomial here. Okay, so let's finish it off. So that means what? Set these factors to what? 0. So 3r minus 2 equal to 0, or r minus 4 is equal to 0. Okay. Here I'm not going to do the algebra, just add 2 and divide by 3, right? So if I add 2 and divide by 3, r will be what? 2/3. Can we see that without too much trouble? Here, add 4 to both sides, r is equal to what? 4. Can we see that? All right, now, again, we need to look at our solutions and compare it to the what? Denominators up here. Do these answers cause the denominator to be 0 in any of these two fractions? Well, 2/3 That's fine. 2/3 minus 1, well, that's not 0, so 2/3 is good. How about 4? 4, that's fine. 4 minus 1, that's not 0, so 4 is good. So both of these answers are valid in this case. So my solutions are 2/3 and 4. Now suppose, so this is my solution for this problem here. But suppose that my two answers are 2/3 and 1. Let's say this 4 was a 1. Then would that have been valid? No, right? Because r minus 1, if you plug 1 in, you get 1 minus 1, which is 0. So that would not have been valid. So in that case, if, for example, if r is equal to 1 here, then we have to cross it off. That's not valid. Okay. However, though, the 2/3, in this case, the 2/3 and the 4, both our answers are valid, and that's our solution here. Okay. Let's look at two types of application problems that we're going to have on the homework. Let's look at the application problems. Now, one type we haven't seen, and the other type we've seen before. So let's focus on the first type then. First type problem we'll see is the work problem. All right, this type of problem involves two parties at work, and we want to calculate if they work together on a project, how long it takes them to complete the project or complete a certain job, for example. This is the new concept we want to focus on. All right. How about the uniform motion problem? We've seen that in the past, but with a slight twist to it. So let's look at uniform motion. This involves an object in motion. This involves a distance equation. If you recall that distance is equal to rate times time, but we're going to modify that just a little bit for the problems on the homework in this section. All right. So let's go back to the work problem. Let's talk about the work problem. Let me give you an example of work problem, or actually let me give you a little small problem here that I want to explain the concept behind the work problem. All right. So let's take a look at this. Okay, so let's say, suppose it takes a student 10 hours to complete a chapter's homework, which is a pretty hard chapter we're studying right now, right? How much of the job is completed after working just 1 hour? And how much of the job is completed after working 7 hours? So let's answer the first question, right? So, well, now if it takes you 10 hours to do the whole enchilada, to do the whole job, which is finish the chapter's homework, then we're simply going to divide it by 10 to complete, to find out how much work you do in 1 hour. In other words, since it takes you 10 hours to do one job, in this case complete the chapter's homework, then how much of the job you've completed after just 1 hour is simply going to be 1/10 of the job. Let's make sure we see that here. Right, so in other words, after 1 hour, I can only finish 1/10 of the job if it takes me 10 hours. All right. Now, how about after 7 hours? Well, then, as you might guess, then it'll be 7/10 of the job. Now, but let's talk about the significance of this concept here of working here, right? Now, especially the first question: how much of the job is completed after working 1 hour? Well, so again, the answer was 1/10 of the job, right? Now, this turns out to be the work rate. This turns out to be the student's efficiency in this case. So if it takes a student, some student may take only 8 hours. In this case, it will be 1/8 of the job per hour. All right. So how much you can complete per hour in this case is your work rate, right? Or in other words, how much one can do per unit time. Now in this case it's per hour, but it could be what depends on the application problem, right? It could be per minute, it could be per second, it could be per day, per week, and so on and so forth. Depends on the problem, right? In this case, we're talking about hours as our time, right? So again, the key is what? How much you can do per hour, or how much one can do per hour, is one's work rate, right? So again, keep that in mind. Let's look at the work rate concept in more detail. So let me go and clear out this screen. That the work rate, in other words, this is how fast I can work. Work rate is amount of job completed per unit time. Per unit time. Now, what does that mean per unit time again? That means what? Per hour, per day, per minute. It depends on the application of the problem. All right. So in the previous screen, I can do 1/10 of the job per hour in this case, right? So my work rate, how fast I can work, is 1/10. So work rate is defined as amount of job you can do per unit time, right? So in the previous example, then 1/10 is the work rate. So if it takes me 10 hours to do a job, my work rate is what, 1/10. All right. Now, well, let me change the problem around. Let me say that suppose it takes let's say suppose it takes 15 hours to do a job. All right. Suppose it takes me 15 hours instead of 10 hours. So what's my work rate now? Okay, well, as you might guess, if it takes you 15 hours to do a job, it takes me 15 hours to do a job, then how much can I do in 1 hour? Again, work rate is how much you can do, what, per unit time. In this case, per hour we're talking about, right? So if it takes me 15 hours to get the entire job done, then how much can I do in 1 hour? That's what work rate is, right? How much can I do in 1 hour? It'll be 1/15, right? I can do 1/15 of the job in 1 hour, right? So now I want you to see a relationship then. What is the relationship between how long it takes you to do a job versus your work rate? Well, can we see that the relationship is what? Reciprocal. In other words, the work rate is always the reciprocal of how long it takes you to complete a job. So if it takes me 15 hours to do a job, my work rate is 1/15. What if it takes me 20 hours to do a job? That'll be what? 1/20. Or again, work rate is equal to what? Reciprocal of how long it takes us to do a job by ourselves. Okay, does that make sense? All right. Work rate again is equal to reciprocal of how long it takes you to do a job by yourself. Okay, keep this concept in mind. All right. So so let me go and write that even. So work rate, one's work rate is equal to the reciprocal of how long it takes to do a job by oneself. Okay, so again, if it takes me 15 hours, then what's my work rate? Reciprocal of 15, 1/15. All right, so keep that in mind. All right. So that's a key concept here. All right. Now, second question earlier on the screen, I asked how much have I done in 7 hours, and remember my work rate was 1/10 earlier. So and I said how much can I do in 7 hours? And it was what the answer was 7/10 earlier in the screen. So you might want to replay that in this video if you need to. All right. But I want you to see the concept as well. So earlier the work rate. So let me say earlier example, okay? I'm not talking about the 15 anymore, I'm talking about the 10 hours now. Earlier, the work rate was equal to 1/10, right? So the question is, how much can I do in 7 hours? How much of the job is done in 7 hours? And the answer was 7/10, all right? Now, I want you to see a concept here as well. So how do I get 7/10 relative to the work rate? Well, here's what I want you to observe. Let's observe that work rate 1/10 times 7 is equal to 7/10. Let's observe that. Now, why am I writing this out instead of just 7/10 itself? Well, I want you to see this concept here, and that is the work rate. In other words, your work rate. In this case, 1/10 is our work rate. Work rate times what? Times time, 7 hours, all right, is equal to 7/10. This is how much of the job you complete. This is the part of the job completed. Again, let me say the formula again. Work rate, 1/10, right, times time worked. This is 7 hours, so this is the time worked, is equal to what? The part of the job that we complete. Right? So let me clear out this here, write that equation here. Okay? So again, we're saying what? We're saying work rate. So one's work rate times the time you put in, time worked, is equal to what? The part of the job completed. Okay, can we see that again? Work rate times time worked is equal to the part of the job that you complete. So in other words, if I work for 7 hours, then my work rate is going to be 1/10 times 7. My time worked is 7 hours, which is equal to what? I finished how much of the job? I finished 7/10 of the job. So earlier we had that. All right. So I want you to solve work problems using this formula in a table format. All right. So let me give you a typical work problem. So let's try this one. All right. So this says what? It takes Erin 30 minutes to shovel the snow off her driveway by herself, all by herself. All right. So if she worked by herself and shoveled the snow off the driveway, it'll take her half an hour. All right. Now it says what? Erin's son can do the same job by himself in what? 45 minutes. So Erin's son's a little slower than mom, for example. All right. So Erin's son can do the job by himself in what? 45 minutes. So if he worked all by himself to shovel the snow, so the job is what? To shovel the snow off the driveway, right? Then the son can do it in what? 45 minutes all by himself without any help. All right. The question though is this: how long would it take to shovel the snow off the driveway if both of them work together? All right. So if Erin and her son work together on this job, then how long would it take? All right. Well, let's think about this for a second now. Okay. Would the answer be less than 30, more than 30, or what? Or more than 45 even? Keep in mind, they're both working together. Imagine two people shoveling snow off the driveway side by side. All right. So they're working together now. All right. So wouldn't it make sense that the answer, if they're working together, is going to be faster than what Erin can do all by herself? In other words, if Erin can do this job by herself in 30 minutes, with her son's help, shouldn't the job get done in less than 30 minutes? Can we see that? Does that make sense, right? Because she's getting help, right? If she's doing it all by herself, she takes 30 minutes. But with the help of her son, then she should be able to get the job done in what? Less than that. All right, can we see that? So therefore, the answer to this question should be less than 30 minutes. In other words, if two parties work together, all right, then the time it takes them to complete a job should be faster than the fastest person. In other words, the fastest person to do the job is Erin. She can do it in 30 minutes. Her son takes, what, 45 minutes. So her son is slower, and Erin's faster, but working together, the time should be even faster than the fastest person. So it should be less than 30 minutes. So we see, otherwise, why ask the son to help, right? It makes no sense then, right? Just have Erin do it all by herself. All right. So again, the answer to this question should be less than 30 minutes. Is what I'm trying to say. So hopefully we can see the logic in that. All right. Now, how do I set this up? Well, I'm going to set up in the table format using this equation here. So let's make a big table here. All right, let's take our time on that. Let's make a huge table here. All right, just like we did before for the word problems we've seen in the past. Right. Let's make a table with 3 rows in it. All right, let's put this equation in. Now, I'm going to do a little bit differently from your book. I'm going to throw in one more column. Aside from putting this equation in, which I will in a moment, let me throw in one more column. Let me call this column time to do a job alone. Okay, so let me call this column time to get the job done all by the person himself or herself. All right, time to do a job alone. Sorry for the handwriting again. Time to do a job alone. All right, can you see that? So I'm going to throw in this additional column, and I'll tell you why I want to throw it in a moment. All right. Now, next few columns, I'm just going to put in this equation. So work rate. All right, take our time on that. Work rate. All right, times the what? Time worked. Okay, how much time we put in? All right, running out of space there, but this last column is equal to what? The part of the job completed. In other words, we're going to calculate. All right, we're going to calculate how much of the job each person contributes to this task. In other words, how much does each person complete? So, for example, Erin might do 60% of the work. Her son might do 40% of the work, right? So we want to figure that out. All right, can we see that? Okay. So again, to figure out the last column is not too difficult because the last column again is what? Is a product of the previous 2 columns, right? So work rate times time worked is equal to what? part of the job that's completed. All right. So again, the last column is what? The product of the previous two columns. All right. The only thing different from the book I throw in is right here, this column here. The time it takes a person to do a job all by himself or herself. All right. Now, what goes in these two boxes? Well, you may have figured it out already. The parties at work. And again, these two boxes, we put the parties at work. In this case, Erin and her son. So Erin and son. All right, and her son. Okay. Now, how long does each person take to do a job all by themselves? Well, it says Erin takes what? 30 minutes to shovel the snow by herself. So she'll take 30 minutes in this job, right? How about the son? Well, the son can do the job by himself in what? 45 minutes. So the son takes 45 minutes. Can we see that? So that's where those two numbers go in, right? How long each person can do the job all by themselves? Erin takes 30 to do a job by herself. Her son takes 45 minutes to do the job by himself. All right? Make sure we see that. Now, what's the work rate? Well, we mentioned work rate earlier. It says what? That's the reciprocal of how long it takes you to do a job by yourself. So if Erin takes 30 minutes to do a job all by herself, her work rate is going to be what? 1 over 30 in this case. All right? Again, work rate is how much she can complete per, in this case, per minute. Right? We're talking about minutes here. All right? The time is minutes. All right? So the work rate, again, the work rate column is just what? The reciprocal of this time alone column to do a job by themselves. Can we see that? All right? So work rate, so if Erin takes 30 minutes to do a job by herself, her work rate is 1 over 30. If her son takes 45 minutes, what's his work rate? 1 over what? 45. Again, just reciprocal, right? No big deal. Can we see that? All right? Now, what is the time worked? Well, how much time did each person put in? Well, we don't know that, right? In fact, that's what we're trying to find out. So that's what? How long would it take to shovel the snow off the driveway if both of them work together? So let's let that be T. So in other words, let's let T be the time it takes, all right, to get job done working together. Again, let's be clear on what the variable stands for, right? So we're saying let T be the time it takes to get the job done working together. In other words, if Erin and her son if they shovel the snow, if they each work for 10 minutes, if they shovel the snow for 10 minutes, then the job gets done. Again, this answer should be less than 30, as I mentioned earlier. All right. So we're saying what? Erin puts in T minutes, her son puts in T minutes, job gets done. Can we see that? All right. So let's say the answer was 15 minutes, for example. Right. So that means if Erin and her son both shovel snow simultaneously, working side by side for 15 minutes, the snow gets shoveled off their driveway. Job complete. All right. Can we see that? Okay, make sure we see that now. So these problems are a bit challenging here, but once you get used to it, it's not too bad. All right. Again, how do I calculate the last column? Just multiply the previous two columns here. So 1 over 30 times T, that's T over 30. Can we see that? 1 over 45 times T, that's T over what? 45. Can we see that? In other words, we're saying what? We're saying after T minutes, Erin does this much of the job. After T minutes, her son does this much of the job. So this is Erin's contribution to the job. This is her son's contribution to the job. Can we see that? But together, they finish the entire job. Notice, there's only one job to do, right? So together, they finish 100% of the job. In other words, Erin might do 60% of the work. Her son does, what, 40% of the work. So 60%, 40%, 100%, the job gets done. Can we see that? So what I'm suggesting here is that the part that Erin completes, T over 30, all right, plus the part that her son completes, T over 45, will be equal to what? The entire job, 100% of the job. So that means what? One job. All right, again, the part completed by Erin plus the part completed by the son, 45 here, all right, is equal to what? One entire job. All right, can we see that? So there you have it. That's the equation we come up with for this type of problem. And let's go and solve it then. What is the LCD of 30 and 45? All right, let's think about this for a second. All right. All right. So hopefully we see the LCD is going to be what? 90. All right. So LCD is equal to what? 90 in this equation. Again, I'm just solving this equation. The word problem part is over once I get the equation. All right. The hard part is getting the equation. Easy part should be solving it. So let's multiply 90 to both these fractions and the 1 to get rid of these two denominators. All right. So I'm going to get what? I'm going to get 90 times T over 30. All right. Plus 90 times T over 45 equal to 1 times 90. Again, I'm multiplying 90 to what? To everything. Can we see that? All right, so I'm running out of space here, but I'll do the best I can to fit it in here. So 30 into 90, how many times? 3 times. So I'll give you what? 3t, then continue up here. 3t, all right? And 45 into 90, twice. That gives me 2t. All right, can we see that? And that's equal to what? 1 times 90 is what? 90. Not too bad. 3t plus 2t is what? 5t equal to 90. Dividing both sides by 5, what's t going to be if I divide both sides by 5? Well, 18. All right. So the answer is what? T is 18. 18 is what? The time it takes to get the job done working together. So in other words, if Aaron and her son shovel snow off the driveway for 18 minutes side by side, the job gets done. Again, 18 should be less than 30, which it is. Right. So the answer is 18 minutes in this problem. Okay. So again, let's take our time on that to figure it out. Okay. So again, we use this table. So practice this table here. Right. The only thing different I'm throwing in here is this column here. The time it takes each person to do the job all by themselves. This is the time to do a job alone, working alone, that is. All right. So again, what's the relationship between work rate and this column? Reciprocal. Okay, make sure we see that. Okay, let's try another problem. Let me go and clear off the screen. Let's go and try another problem. Hang on a second. My sketch pad once again is acting up on me. Okay, so let's go ahead and try this one. Okay, so here's the problem. So working together, Pat and Chris can complete a landscaping job in what, 6 hours? All right. Working alone, Pat can do the job in 15 hours. How long would it take Chris working alone to do the same job? All right. So the job here is to do some kind of landscaping work. All right. Now, if Pat and Chris work side by side again, the job gets done in 6 hours. So that's given to us. All right. But we're not being asked that. What we're being asked is, if Chris worked all by himself in this job without Pat's help, then how long would he take to get this job done? All right. So again, let's make a big table here. Set this up. Okay. So all right, let's take our time on that. Again, the first column is going to be what? Time. I'll just say time alone to abbreviate, all right, if you don't mind. Time alone means what? Time, how long each party takes to do a job all by themselves. But that's what I mean by time alone. The time it takes them to do a job working alone. Okay, that's what we're talking about. All right. So let's put the equation here: work rate. All right. Times the time worked, or I'll just say times time. Okay, instead of time worked. All right, is equal to the part completed. Part completed. In other words, the part of the job that's complete. All right. How much does each person contribute to this job? All right. Again, just multiply these two to get the last column. All right. Make sure we see this concept here. All right. Again, what parties are at work? Well, Pat and Chris in this case. So Pat and Chris. Let's fill out one column at a time. Anything we don't know, introduce a variable. All right. How long does Pat take to do a job all by himself? Well, it says what? Working alone, Pat can do the job in what? 15 hours. So look for that information in the word problem. You may have to read the word problem more than once, but take your time on that, all right? So again, it says what? Working alone, Pat can do the job in 15 hours. So Pat will take 15 hours to get this job done if he worked by himself, all right? How about Chris? How long does he take if he worked by himself? Well, that's what we're trying to find out, right? That's what? How long would it take Chris working alone to complete the job? Well, we don't know that. That's what we're trying to find out. Let's make that T, all right? Let's assume Chris takes T hours to get this job done, this landscaping job, all right? If he worked by himself, all right? So work rate is what? Reciprocal of these two, right? So work rate for Pat, 1 over 15. All right, that's a 5 there. Sorry about that. Work rate for Chris, 1 over what? 1 over T. All right, make sure we're good on that. How about the time? Well, the time worked to get the job done. Well, what do we know about that? It says what? Working together, Pat and Chris can complete a landscaping job in 6 hours. Can you see that? In other words, if Pat and Chris work side by side for 6 hours, job gets done. So that means Pat's going to put in 6 hours. Chris is going to put in 6 hours. Side by side, job gets done. All right, can we see that? So how much does each contribute? Well, Pat will complete what? 6 over what? 6 over 15 of the job. All right. Chris will complete what? What's 1 over T times 6? 6 over T. All right, can we see that? All right, let's do one additional mathematical thing here. Look at 6 over 15. Can I reduce that? Yeah, I can reduce that, couldn't I? Because 3 goes into 6 and 15. Can we see that? 3 into 6 what? Twice. 3 into 15 what? 5 times. So isn't that 2/5? 6 over 15, isn't that 2/5? All right. So what we're saying is what? Pat in 6 hours completes what? 2/5 of the job. That means Chris has to complete the other 3/5 of the job. Can we see that? So Chris completes the rest of the job. So let's set it up. So Pat's contribution is here 2/5. So 2/5, all right, plus here's Chris's contribution. 6/t, all right, is equal to what? Again, if you put their two parts together, it's equal to 100% of the job. One job. One job means 100% of the job. Can we see that? So typically you set it equal to 1 then for these types of word prompts, right? These work prompts here. All right? Okay then. So let's go ahead and finish off this. What's the LCD then? Well, LCD hopefully we see is what? 5 and t, so 5t. All right? So let's multiply everything by 5t. So 5t times 2/5, all right, plus 5t times 6/t equal to 1 times 5t. Okay, are you with me on that? Multiplying LCD to everything, all right? So what do we get? Well, 5's drop off, so t times 2 is what? Let me continue. Yes, fine, I'll continue now. So that's going to be what? 2t, all right? T's drop off here. 5 times 6 is what? 30, equal to what? 1 times 5t, 5t. All right, can we see that? Let's get the t over to the right side. Let's subtract 2t on both sides. And so hopefully we see the algebra without too much trouble there. 2t's drop off, so I have 30 equal to what? 3t. All right, so dividing both sides by 3, what's t going to be? That's a 3 there. Sorry about that. Let me, sorry, having trouble with the sketch pad again. So that's a 3 there. Sorry about that. So that's a 3 here, okay? So 3's drop off, 30 divided by 3. Sorry for sloppy 3 down here. But 30 over 3 is what? 10, right? So t is equal to 10, all right? What's t though? T is how long Chris takes to do a job all by himself. Time alone. Time to get the job done working alone, right? That's t. So Chris takes t hours. That means what? If Chris had to do this job all by himself, Chris would take 10 hours. So he's actually working faster than Pat, as you can see. All right? So the answer is 10 hours. That's how long Chris would take if he's working all by himself. All right? So the key is to fill out this table. Once you get these two parts here, you add them up. You set it equal to what? 1, because these two parts add up to the entire job, 100% of the job. Right? Hopefully we see the logic in these two problems here. All right? Now, let's look at the other application problem that we've seen before. Let's look at uniform motion. Let me clear out the screen here. If you recall the uniform motion problem, involves the distance formula. D is equal to rate times time. Distance is rate times time. All right? Now, we're going to do it a little bit differently in this section because the word problems in this section, the distances are given to you. All right? So what we're going to do is let's solve this equation for t. So how do I get t by itself here on the right side? Well, divide both sides by what? By r. Can we see that? So therefore, time is equal to what? Distance divided by what? Rate. All right? Again, time is equal to distance divided by rate. All right? So our table setup will be like this. Okay, I'll give an example for you in a moment. All right? But hang on just 1 second. So our table setup will not be rate times time is distance. It'll be what? Distance, all right, divided by, so division here, divided by what? The rate. Okay, distance divided by d over r, right? Distance divided by rate is equal to what? Time. Okay, sorry, I ran out of space here. Again, the table says what? Distance divided by rate equals time. Okay, I'll make a nicer table here in a moment. All right, let's go and try a word problem involving this table. All right, again, so you fill out the distance column first, then you fill out the rate column. You divide these two to get the time of travel because time is what? Distance divided by rate, as you can see here. All right, can we understand that? All right, let's go and try a problem. Let me go and clear out the screen. Let's look at this example here. Okay, let's use that table. Okay, so it says what? The president of a company traveled 1,800 miles by what? Jet and 300 miles on a helicopter. All right. The rate of the jet was 4 times the rate of the helicopter. All right. The entire trip took what? 5 hours. Find the rate of the jet. So I want to know how fast is this jet going at. All right. So let's go and set it up. So let's make a nice big table here. All right, so 3 rows in it. Okay, so let's set it up. All right, so let's look at that. So we have what? What's the table say? Distance. Again, I mentioned that earlier. Distance what? Divided by the rate. Okay, is equal to what? The time. Okay, are you with me on that? So we're changing the table a little bit, right? D over R. D divided by R is equal to T. All right. Make sure we see that. All right, then. What goes in here? Well, the two objects we have in this problem. What is it? By what? Jet, and by what? Helicopter. So we have a jet, and we have a copter. All right, can we see that? All right, the distance. What is the distance traveled by each object? Well, it says what? The president of the company traveled 1,800 miles by what? By jet. Okay, fill out one column at a time. Reread this problem several times if you need to get each row, each column filled out. All right. So it says what? Travel 1,800 miles by jet. So the jet's distance is what? 1,800 miles. Are you with me on that? All right. How about the helicopter? Well, this president flew 300 miles on a helicopter. So the distance covered by the copter, 300 miles. Can we see that? Not too bad. All right. Here's where the variable comes in, the rate. It says what? Rate of the jet is what? 4 times the rate of the helicopter. All right. 4 times. But I don't know how fast the helicopter is going at. So let's make that R miles per hour. Or let's make the rate for the helicopter R miles per hour. But the jet is going to be 4 times that. So what? 4R. Can we see that? All right. So therefore, the time for the jet, the time of travel on the jet is what? Distance divided by rate. Again, the last column is what? By dividing these two previous columns. So 1,800 divided by 4R. So 1,800 over what? 4R. Can we see that? Now let me reduce that fraction though, because I can reduce that, right? Because 1,800 is divisible by 4. Let me punch on the calculator. 1,800 divided by 4. My calculator is what? 450. So this is really going to be what? 450 over R. Can we see that? Because 4 into 1,800, how many times? 450 times. Sorry for that small 450 there. All right, can we see that? Just reduce this fraction. That's all I'm doing here. 450 over R. All right, punch into calculator. All right, how about this one? What is the time on the helicopter? Well, 300 divided by R. 300 over R. Okay, sorry, I ran out of space there in that table. So 300 over R is what? The time on the helicopter. 450 over R is what? The time on the jet. Now, what do we know about time? It says what? The entire trip took what? 5 hours. Right? That's the entire trip. That means what? The time on the jet plus the time on the helicopter is equal to what? 5 hours. So the equation we're solving is going to be 450 over R, time on the jet, plus the time on the helicopter, 300 over R, equal to what? 5 hours. The entire trip took 5 hours. So 5. All right, are you with me on that? All right, so let's go and add them up. So, well, actually, now I can multiply by LCD once again, but look, these two fractions are the same denominator. Just combine them. What's 450 plus 300? Well, that's 750 over R equal to 5. All right? Now, we haven't solved too many equations with the variable on the bottom, but what you want to do when you have a fraction is get rid of that denominator. So get rid of the R. How do I do that? Multiply both sides by R. Okay, take the product of both sides by R. Okay, multiply both sides by R. So R's drop off here on the left. Can we see that? So I get 750 is equal to what? 5R. All right? Dividing both sides by 5 now to solve for R. Can we see that? What's R going to be? 150. 750 over 5. 150. All right? 150 miles per what? Per hour. All right? This is the speed of the what? Well, that's the speed of the what? Helicopter, right? But what I want that's a fast helicopter, all right? What I want the speed of the what? I want the speed of the jet. Let's find the rate of the jet, all right? So what do we know about that? Well, the jet speed is what? 4 times that, right? The rate of the jet was 4 times the rate of the helicopter. So therefore, the jet speed is going to be 4 times 150, which is what? 600 miles per hour. This is the rate of the jet. And rate of jet. So the solution we're looking for is right here. 600 miles per hour, rate of the jet. All right, can we see that? Again, use this table. Distance divided by rate is equal to time for the uniform motion problems in this section here. Let's try another one. Let me clear out the screen. All right, let's look at this example here. Okay, so it says what? It says a cruise ship can sail 28 miles per hour in calm water. Calm water means what? No current. All right, sailing with the Gulf Stream. That means with the current. All right, the Gulf Stream is the current. The ship can sail 170 miles in the same amount of time as it takes to sail 110 miles against the Gulf Stream, against the current, all right? Find the rate of the Gulf Stream. So let's make a big, nice table here. Okay, I'll make a bigger table than the last one, okay? Since I ran out of space in the last one. Hopefully I won't do that here. Okay, so let's put that in. So again, distance, all right, divided by rate okay, is equal to time. Okay, you practice this table here. All right. What two situations are we comparing here? Well, look, sailing with the current, sailing with the Gulf Stream, and what? Against the Gulf Stream. So let me say with stream, I'll just say with stream, meaning Gulf Stream. So that means what? With the current, right? Okay, and against stream, which is what? Against the current, against the Gulf Stream, all right? So, again, it says what? The cruise ship can sail what? 28 miles per hour in calm water. So when there's no current, it can go 28 miles per hour, all right? Now, first of all, let's work on the distance, though. How far do we go with the Gulf Stream? It says what? The ship can sail 170 miles. It says sailing with the Gulf Stream, the ship can sail 170 miles. So 170 with the Gulf Stream, all right? How far can we go against the stream? It says what? In the same amount of time as it takes to sail 110 miles against the Gulf Stream. So 110 is the distance against the stream. Can we see that? Again, take your time to read this problem over and over again until you see these two numbers for these two situations. All right? What is the rate then? Well, now it says what? Again, it says the ship can sail 28 miles per hour in calm water. All right? So therefore, the rate. Now it says what? It says find the rate of the what? Of the Gulf Stream. So that's what I'm going to find out. Let's let that be R. Let R be the rate of the current. Rate of Gulf Stream, which is the current. All right? So if I can go 28 miles per hour in calm water, and I'm going with the current, that means I'm what? I'm going faster, right? So my rate is 28 plus R. Can we see that? It's helping me go faster, right? Against the current, slowing me down. 28 minus R. Can we see that, all right? So again, what is the time with the current and against the current? Well, divide. Distance divided by rate. So this is 170 over 28 plus R. This is what? 110 over 28 minus R. Can we see that? All right? Now, what do we know about these two times? Well, look what it says here. It says sailing with the Gulf Stream, the ship can sail 170 miles in the same amount of time as it takes to sail 110 miles against the Gulf Stream. So same amount of time. That means these two times are what? Equal to each other. Remember, last problem was what? The entire trip took 5 hours, right? So, and we add up the times because of that. This time we're told these two times are equal. Same amount of time. Key words there, okay? So therefore the equation we come up with here in this problem is 170 over 28 plus R equal to 110 over what? 28 minus R. All right, can we see that? That's the equation we have to solve. And look at here. One fraction on this side, one fraction on this side. What's that? Proportion. Well, proportions, remember, are easier to solve than the other rational equations, right? We just what? Cross multiply. Can we see that? Let's do that. So let's go and take the cross product here. Let's cross multiply the 28 plus R times 110. So this will be what? 110 times 28 plus R equal to 170. So the cross products are equal, right? 170 times what? 28 minus R. Can we see that? All right. Let's work it out. Use your calculator. 110 times 28. So 110 times 20 in my calculator. It's going to be 3,080. Okay. 110 times R, 110 R. Just punch in the calculator. All right. 170 times 28. 170 times 28. 4760. 4760. And then 170 times negative R minus 170 R. Okay. I'm just solving this equation. No big deal. All right. Let's get R's on one side, numbers on the other. So let me get R's on the left, numbers on the right. Okay. Are you with me on that? Okay. So let's go ahead and do that here. Let me fix my sketch pad. Okay, so let's go ahead and do that. So let's go ahead and add 170R on both sides, if you don't mind then, to get it on the, what, left-hand side, okay? Takes care of that, all right? So this will be what? This will be 280R, but again, let me combine a couple of steps if you don't mind. Let me bring the 3080 onto the right side. So let me subtract it out. 3080 minus it out. Minus 3080. Okay, so that takes care of that. So again, 110 plus 170 is what? 280. So let me consider here. I ran out of space down there. Well, let me just write down here. 280R. Okay, you can see it a little better perhaps. So 4760 minus 3080. Just punch on the calculator. We get 1680. So that's going to be 1680. All right. So what do I do? Well, let me copy the equation up here since I really ran out of space down here, as you can see. So I get 280R equal to 1680. Can we see that? And hopefully you see the algebra clearly here, okay? Dividing both sides by 280. So divided by 280 on the calculator, we get 6. R is equal to 6 miles per hour. This is the rate of the what? Gulf Stream, rate of the current. This is the solution we're looking for in this problem. Okay, can we see that? So again, use this table to set up the uniform motion problems. Distance divided by rate equals what? Time. Fill out one column at a time. Look for those key pieces of information I've underlined here. All right. So let's go ahead and give a couple of problems to post the solutions to in the discussion area in Blackboard. So let me go and clear off the screen here. All right. So let's go and post these solutions to these problems. All right. Let's take a look at these two questions I want you to post these solutions to in the discussion area in Blackboard. All right. Number one, a word prompt. One grocery clerk can stock a shelf in 20 minutes. A second clerk requires 30 minutes to stock the same shelf. How long would it take to stock the shelf with both clerks working together? So they work together. How long would they take? Again, the answer should be less than 20 here because if they're working side by side, it should be faster than the fastest guy. All right? So make sure we see that. So use that work problem table to set it up. Again, work rate times time is equal to what? Part completed. All right? Number two, uniform motion. A plane flies 460 miles per hour in calm air. Flying with the wind, the plane can travel 1,560 miles in the same amount of time. Again, there we go again with that it takes to travel 1,200 miles flying against the wind. This is very similar to that cruise ship problem we did earlier. All right? Find the rate of the wind. Okay, so again, so you can set it up. The setup is almost identical to that cruise ship problem. Okay, so again, post the answers to these two questions in the discussion area in Blackboard, and we'll go over the word problems in class. So until next time, bye-bye.